My name is Alex, and this is my report for Lab 2. So the purpose of this lab was to observe the magnetic field of a bar magnet and understand how distance affects the strength of a magnetic field. And then I simulated the magnetic field of a bar magnet through GlowScript and compared the simulated and experimental magnetic fields. The results show that the magnetic field increases as distance decreases, and then I calculated a magnetic dipole moment of 0.1225 amps meter squared. The measured off-axis magnetic field was 3.126 times 10 to the negative 5 Tesla, while the simulated off-axis magnetic field was 4.276 times 10 to the negative 6 Tesla. So some key concepts are the Biot-Savart law, which describes how an electric current creates a magnetic field, and it shows the dependency of the magnetic field on the current and the distance to the observation location. And it can be used to describe the magnetic field of a ring of current, which is a magnetic dipole, and similarly so is a bar magnet. And so we can use that equation to find the magnetic field produced by a bar magnet. So magnetic dipoles, the magnetic field of a magnetic dipole is analogous to the E field of an electric dipole. And they have a magnetic dipole moment, which we denote through mu, and we can use this to determine the magnetic field produced by a magnetic dipole. So here's just a diagram showing the system, which is the observation point, which is also where the magnetometer is located in the phone, and the surroundings is the bar magnet. As you can see, mu points from north to south. So the procedure is, first we had to align the phone to Earth's magnetic north axis, which I did by rotating the phone so that the x component of the magnetic field was closest to 0. And then I had to locate the magnetometer chip, which I did by moving the phone left and right while it was vertical, and to reduce and minimize the x component of the magnetic field. And then I rotated the phone horizontally and then moved it left and right again to minimize the y component, and where those two places intersect is where the chip is located. And then I determined the on-axis magnetic field, and then determined the off-axis magnetic field. So the data results are shown here, and as you can see, through the determining the on-axis magnetic field, I created this graph which shows a linearized relationship between the natural log of the x component of the magnetic field versus the natural log of the distance. And so using that, we can determine the magnetic dipole moment. And so we know that ln k is the y-intercept from that relationship found earlier. And so doing that, we can solve for k, and then k is from the Biot-Savart law equations, we know is equal to mu naught over 4 pi times 2 mu. And so we can solve for mu to get 0.1225. So then this is the code for the computational model. First, I had my constants, and then created my function to determine the magnetic field. And then I created the errors and determine the magnitudes of the magnetic field at different observation locations on axis and perpendicular. And then to determine the off-axis B field, this is the code for that. And then this is the visualization and results. So from this experiment, we saw that when the magnetometer is far away from the magnet, it measures near zero magnetic field in the x direction. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Some sources of error, because the values that I got for mu, both simulated and measured, were very different. And so this could be due to like initial misalignment of the phone with Earth's magnetic north, any excessive movement of the phone while conducting the experiment, presence of external magnetic fields besides the Earth and the bar magnet from like other electronics around me, and also measurement errors of like the distances, or just errors in the magnetometer app. By aligning the magnetometer chip with Earth's magnetic north, we could separate the effects of the Earth's magnetic field from the effects of the bar magnet's magnetic field. And so if we hadn't done that and we had just laid out the meteor stick at some intermediate angle, then the x and y components would change because they would include some sort of contribution from the Earth's magnetic field. If you had two identical magnets stuck end to end, the direction of the magnetic field wouldn't change, because if you had north on the left and south on the right, you would still have that with the two magnets. However, adding the second identical magnet would increase the magnitude of the magnetic field by roughly a factor of 2.